Okay, let's complicate things a little bit and let's move from a single phase generator to a two-phase generator. And so we're going to take that same idea that we had in coming up with a single phase generator, and we're going to basically add another coil and make two phases of electricity and see what happens when we do that. Of course, what we're working toward is the three-phase generator, and we'll take the next step now. Okay, working off of this same idea, right? Coil, rotating magnetic field, voltage generated, load connected to the coil, current starts to flow, we get voltage and current. We graph what we call the power curve there, right? Okay, so now what we're going to do is we're going to take this same idea, and what we're going to do is we're going to add a second coil to this construction. So here's our winding A still. So here's A1. And now we're going to come 90 degrees around, and we're going to add another coil. Remember, these coils, they run the length of the stator. They terminate on the other side. So now we have a winding A and a winding B. Of course, those are laid into slots that are cut into the stator. Now, of course, it makes sense that since these two coils are mechanically 90 degrees apart, right? The voltage that's generated is going to also be 90 degrees apart. All right, so when I look at this, let's see if we can find a good place on this graph to look at this. Okay, so here's EA1, and it's peaking there at 0 degrees, right here. And then if I come out 90 degrees later, there's EB2, and it is peaking 90 degrees after that. So it just follows the same mechanical construct that, the electrical outputs, are the same as the mechanical construction of this machine. And that's pretty an interesting idea in and of itself. And so, we see this relationship here, and we see the two phases, and we see how the peaks are 90 degrees apart as we walk through this thing. Okay, so that's kind of an interesting thing. And I guess the next thing that we might want to look at is, let's get used to some of the representation of these things as we start to come up with the symbols for electrical machines. So this is supposed to represent the coil A1, and here is coil B2. And then we see from this phasor diagram that EA1 is 90 degrees in front of the voltage that's generated from EB2. And again, we can see that in the curves that result from this, okay? So, and we're seeing the correlation between the mechanical construction of this and the electrical output from that. And then, as I looked at this, let me clean this up some. If I'm here at winding A, and this rotating magnet is at that point, then the maximum flux is being presented to coil A, and that's why you're going to see it peak at that point. And then as I rotate, if you can imagine this magnet moving to this position, then coil B is at that point going to see its peak voltage. And of course, this is going to continue to repeat itself as we continue to roll through. We go 90 more degrees to here, and we're getting a negative peak out of A1. And then we go 90 degrees from there to here, and we get a negative peak on coil 2. All right, so we'll say, to sort of summarize this, that the voltages are 90 degrees out of phase, that EA1 becomes positive or peaks 90 degrees before EB2. And then, so, you know, that's the thing that we're looking at this point. We call this machine a two-phase generator. And then the stator windings are, you know, respectively phase A, this is phase A, and this is phase B. And then we've got a little problem that we can look at here. He says the generator shown in figure 8.6a, this guy right here, is, this is our example. Let me clean this up so we'll work this little problem. Okay, and so it says this generator is rotating at 6,000 RPMs. Okay, so this magnet is making a complete, well, it's making 6,000 complete revolutions in 1 minute. And it generates an effective sinusoidal voltage of 170 volts. That's effective. Or another term for that we call this, or it's an RMS voltage, right? And the question says, what is the peak voltage across each phase? Well, that's pretty straightforward. We can easily come up with that idea. He abbreviates it E sub M, I guess E max, okay? I would have been more comfortable with E sub P or peak voltage. But the peak voltage in relation to an RMS voltage, we know that is the square root of 2 times the effective voltage. And 170 times the square root of 2, or 1.414, is around 240 volts, okay? So that would be that problem. You know, we could also, what else could we? We could also, well, I won't get into that, but, you know, either square root of 2 or 0.707, you know the way that works. You remember that from 131, I hope. And the second question on here says, what is the output frequency? Okay, well, the output frequency, it says 1 cycle is completed every time the magnet makes 1 turn. Okay, the cycle is completed every time the magnet makes 1 turn. So if the frequency is 6,000, it's RPMs per minute, right? 6,000 RPMs per minute. How many revolutions would it make in 1 second? Okay, so you think about that for just a second. Okay, so I'm going to show this to you a little bit differently than what he does. But, you know, if we're at 6,000 RPMs per minute, how many revolutions would that be in 1 second? Well, 6,000 revolutions, 1 minute is 60 seconds, right? So the minutes cancel out. 60 into 6,000 it would give us 100 revolutions per second. Frequency is 100 hertz, because that is defined as the number of revolutions per second. And so if I'm trying to figure out the time, that is 1 over F, right? And then 1 over 100 is going to be equal to 0.01 seconds, or as he tells us in the text, 10 milliseconds, right? 1, 2, 3 places, 10 milliseconds. Okay, so, you know, I figured out the frequency first here, right? It's 100 hertz. That's the frequency of the situation, the output frequency that we would have. And then, you know, he calculated the period first. But I want to give you 2 different looks at it, right? One is the inverse of the other. So they both work. And then the last thing he says is, how much time would occur after a rotation of 90 degrees? Well, Okay, so this thing here, I mean, we could do this, or we can reason it out, or we could do it mathematically. Either way. But this magnet here. Let's get some color to this. This magnet is making a complete cycle in 10 milliseconds. So really, all he's saying is, how long does it take for this magnet to go from here to here, to go 90 degrees? All right. And so, no reason to make that overly complicated, but the period of a frequency of 100 hertz is 10 milliseconds. And, 90 degrees is 1/4 of that value. So really, just divide that by 4, and then you would come up with 4 into 10 milliseconds, or 2.5 milliseconds would occur for this to rotate through 90 degrees. Okay, that ought to wrap up 8.4.